Today I'm going to cover force, torque, and strain measurements. What I'm going to go over today is I'm going to start by going over a linear elastic spring first. And then we move on to the next topic. So I'm going to go over what the definition of an elastic spring is. Simply, an elastic spring is a type of a spring that if you pull it to a certain extent, or if you apply the force in which they're causing this elastic spring to deform by an amount y in this case, or delta. This is a little y shown up here. So if originally the spring is at rest and there's no forces applied, that's where we have right here, and then I apply a force F to the end of the spring and I pull it in one direction only, so there will be only translation in the x direction in the form of a displacement. There will be no rotation of the spring, and there will be no y or z translation. So pretty much one end of the spring is fixed, and it is pulled in a linear fashion, making sure that the behavior of the spring is linear. When that happens, then as a result of the force, we would have some displacement. It's a spring, so it has the properties of, in this case, moving right and left to the page. By elastic spring, we are talking about a spring that obeys Hooke's law, and it would go back to its original shape after we remove the force, because if we pull it too much, I'm sure you guys have seen this, if you pull a spring by an excessive amount of force in which the spring cannot really go back to its original shape after we remove the force, that is called the inelastic, meaning that there will be no recovery of the material, the strain of the material. It goes to the inelastic range. The discussion on inelastic range is really beyond the scope of what we cover in this course, but for your information, any material that falls into the inelastic range, then we start talking about the inelastic theories and different types of criteria, including Tresca and von Mises and those type of criteria for modeling nonlinear behavior of the material. So we're not going to get into those. For the sake of our argument, the stiffness of a spring is defined as force per unit displacement, meaning that the stiffness of a spring is defined by a force that causes it to displace by 1 unit displacement. In this case, the force is defined as elastic force. It is given in Newton. We're dealing with metric system. The K in this case, which is called the spring constant, is given in Newton per meter, is following the same definition as I told you. Force per unit displacement, that's the stiffness of the spring, or what we call K. In metric, it's Newton per meter, and then the displacement y, or some books they call it delta. Both is correct. And throughout the lecture today, I'm going to also use y or little delta interchangeably. That is the displacement of the spring from its equilibrium position, and that is before we apply the force F, and that is usually expressed in meter in metric system. So basically what we need to really understand here is that the way we define the stiffness or the spring constant, K is also the stiffness or spring constant is the same. That is force per unit displacement. Secondly, I'm going to go over how we can actually measure the force that is required for any type of an elastic displacement in a prismatic bar. The bar here on the left hand side, it's called bar BC. I'm going to put a little check mark right next to it here. That bar BC is prismatic, meaning that it would have a constant cross section throughout before we apply the force to it. It has a constant cross section, we call that A sub C, and as a result of an applied force F, interchangeably referred to as P, there would be a small amount of displacement. Sometimes it's called deformation, but in this case, since there's no deformation, we call delta as a displacement. So the length of the member BC after we apply the force F, shown on the right hand side, it would be capital L plus little delta. That would be the new length for member BC on the right hand side. On the left hand side, that's before we apply the force, so the length would be L. So the force, and this could be derived from the stress-strain relationship. This force, in this case, we are going to have F, which is again the same as P, would be A sub C times E. E is modulus of elasticity of the material itself. So if this is a prismatic bar made of steel, which is our assumption in this case, E would be the modulus of elasticity of that particular steel. If it is 36 KSI, and E would be as such, and so on. So E here is really a property of the material. And that's not a geometric property. It's the material property. And A sub C is the cross section. That is a geometrical property. We need to distinguish between the two. L is the same way. So both A sub C and L, of course, A sub C is the cross-sectional area as a variable if we increase it or decrease it depending on the sample size. L is also a geometric property, that is the length of the bar, and the delta is the displacement that this prismatic bar would go through after we apply the force F. So the formula that is developed here, A sub C, basically the cross-sectional area of the bar multiplied by its modulus of elasticity when it is divided by the length of the member itself and multiplied by the deformation, or in this case we call it displacement. That would give us the force for this particular the force that's required to move it by a displacement amount delta. In metric system, F is in Newton, A sub C is in square meter, modulus of elasticity is Newton per meter squared, and the displacement is in terms of meter, and L is also length of the bar given in meter. So that's the other useful formula that we will be using to measure the elastic force for a prismatic bar if we know the displacement. All of these principles are used in different types of devices that we have, different types of devices that we use in metrology and instrumentation. We also can have very accurate measurement using the principles of mechanics. If we can measure it using a cantilever beam that is shown here. This is used to measuring the vibration of antennas and other types of devices that's used for measuring, different measurements in different devices. So this is what we call a cantilever beam model. The configuration is shown here. Again, the length of the cantilever beam fixed on, in this case, left-hand side. Why this bracket it's fixed, so that's the assumption there. Of course, the way it's shown here, it may seem that this particular bracket is not going to just fix that, but again, this is connected to other pieces, larger pieces that or either welded, most cases are bolted, in such a way that we would have no displacement at one end. That's the definition of cantilever beam. On the other end, we apply the force F, and as a result of the force F, we are going to have a displacement by the amount delta, not a capital delta, but it is the lowercase delta in the Greek alphabets that we're using here. So this is the shape of the deformed shape of the a line. Pretty much I draw a line here that is on the outer fiber of this beam. So the assumption is if this line moves down by an amount of delta, you can see that every line on this, if it's a rigid body, a rigid prismatic bar, there'll be no deformation of the bar itself under the application of load except at the tip. As such, we can measure this displacement at the tip by dividing F by 3 E sub I L sub 3, or we can calculate the amount of force that's required to pretty much bring it down by a small amount of delta by using 3 times E times I divided by L cubed. All of these formulations are derived from strength of material. There is solid mathematics behind it, and it's also been confirmed by laboratory experiments numerous times. So it's not just a formula given and the question is, well, where did you get that formula? It's all being derived mathematically, and there are tremendous number of references that we can refer you to. So I would be the moment of inertia for in a metric system or cross section. It's meter to the power 4, so meter cubed meter. E is the, again, elastic modulus of elasticity. Again, this is the property of the material itself. Delta or Y is the displacement in meter, and L is the length in meter. So that's another useful formula, and we're going to do some examples. So for different types of cross-sectional areas, or for different types of cross-sections, we're going to have different moment of inertia. And BH cubed divided by 12, this is for a rectangular cross-section. If you switch B and H, this formula is not valid anymore. So you want to make sure that you understand which is which dimension is the H, which one is the B, because if you don't use it correctly here, you would definitely arrive at a different moment of inertia. So if I turn this to its side, you would see that your B and H would be different. That's why this type of a beam, this particular cross-section, has higher moment of inertia than if I flip it to the side and lay it down to its side, the longest member. This one has higher, so it's more difficult pretty much to bend a beam with this cross-section if we apply the load exactly at the tip on top, whereas if you turn it around to the side, more like a ruler type of a thing, then you can easily bend it, and that is because we have a smaller moment of inertia. Again, we are dealing with engineering, and everything has been formulated pretty much, and there is both mathematical principles behind it and also experimental data. In this case, if we substitute in previous equation for I, as shown here, bh cubed b times h cubed divided by 12, force would turn out to be E modulus of, it's modulus of elasticity times moment of inertia, which would replace it by bh cubed divided by, in this case, by 12. So we do the substitution and carry it on the equation. It will be EBH cubed divided by 4L cubed times Y or delta. Remember, this is also this Y here is also shown as delta. It's pretty much the same. So for circular cross section, if it is solid, meaning it's not hollow, that means that we're going to have different moment of inertia, pi times d to the power 4 divided by 64. As such, F would be different. So for different cross sections, we have different moment of inertia. If it's a circular hollow cross section, assuming the outer diameter is shown as d sub O and inner diameter is shown as d sub I, then in order to, we're dealing only with let me find my, we're only dealing with this portion of the beam throughout. This is the solid section. The middle of the beam is really hollow. Okay, at center, circle is pretty much, so we're dealing with the pretty much near the perimeter of the cross section, and all these areas that I'm showing, I'm trying to draw the line inside the solid section of the bar here as shown. In that case, the moment of inertia would be pi divided by 64, d for the outer minus d sub I, so that's the part that's solid, and it's shown here. So F would be, of course, different now. Again, all you need to do is in the original F formula that I developed, we do the substitution for I, and you're going to have different forces. And you can do a little exercise on your own to see, well, if you want to see which cross section is has least amount of displacement at the tip, you can play with this, the F that you can calculate, and you would see that for which cross section you require more force or less force in order to provide the displacement in the end. So there's an example problem I'm going to go over here. And the following is made of, again, the E of the material, 100 gigapascal in metric system. A force of 10 kilonewtons is applied at one end, and the exact geometry, the geometric properties are shown. B and H is given. The length is also given. So we know the geometric properties. We also know the material properties, and we would like to know what would be the resulting deflection, Y or delta, at the end of the beam, or what I call at the tip of the beam. So it's a matter of basically plugging the numbers into the equation for the force that we discussed previously. F is 3 E times I divided by L cubed times Y or delta. F is given in this case, and E is given, H is given, B is given, L is given. So if I want to, let me find this. F is given, E is given. I can calculate it. It's based on it's a geometric property of the cross section. B H cubed divided by 12 for a rectangular cross section. L is given. This is also given. So all I need to do is to calculate that Y. This is the unknown. Put a little question mark over it right here. There we go. Y or delta. So in order to do that, I simply take 3 E times I divided by L3 to the other, divide F by the known part of the equation on the right hand side. I divide the left hand side by that. But first I need to calculate the moment of inertia, BH cubed divided by 12. I know the B is given, H is given, so it's a matter of really doing a numerical substitution. That would be I in meter. Note that everything is given meter for the sake of correct unit calculations. And then I rearrange the formula, and eventually it would, give me the result 0.03. This is the final answer, 0.035 meter. Please pay attention to the number and see if it makes sense. It's 0.03 meter for this particular type of beam. Let me go also over how we can actually measure torque, or what we call a torque measurement. On the right hand side, I provided a little figure. Don't pay too much attention to the numbers that's given, but the whole point is you can have a device like that in which you apply a force of 5 kilonewton at one end of it, and that's the demonstration of a torque. If D is connected to a solid ring that's attached to the end of this particular device or particular bar that's shown, if you have a tendency to push the D down, of course we are going to have what we call a torque. Torque is applied in designing motor shafts. It applied in designing equipment, different types of equipment we use, including certain type of motor-driven screwdrivers, other types of tools that we use that requires certain amount of torque. Of course, we want to make sure the way we design these devices, they're not going to break on the particular application of the torque. So pretty much going back to the shape on the left-hand side, this blue little, this is showing the cross-sectional area of a hollow shaft. Okay, so there is also this little angle phi in this case. Some books they refer to it as theta, what have you. This is the angular deformation that's caused by the applied torque on a bar of L, the length L. This shaft or hollow shaft or bar or hollow bar is made of course, we're going to have the inner diameter of the shaft and the outer diameter. We keep that in mind. So the T, in this case, the torque that's applied is given from the formula. In this case, there is a term G that's probably haven't discussed so far, and the angular deformation that I just showed you. So T would be pi times G. G is the modulus of rigidity. Again, that's another term. If you haven't heard of it, modulus of rigidity, or also called elasticity under shear. That is a measure of measuring how much shear a cross section can take. So G would be the modulus of rigidity would be E modulus of elasticity divided by 2 times 1 plus. In this case, the mu is the Poisson's ratio, which is 0.3 for steel. So knowing the material, we know the Poisson ratio, the material itself. Also, G is given in tabular forms for different cross sections in different types of manuals that we use for the design. So this is the amount of torque that a cross section like that would be able to take. Again, it's a hollow shaft, and that's how we can determine how much torque it can measure. Of course, in the design, real design, we also would incorporate a factor of safety that could also be already incorporated in some of these measurements, including Poisson ratio and modulus of elasticity and so on. So there will be many. So it's kind of like a factor of safety on top of a factor of safety on top of another factor of safety, making sure that our devices would actually, they won't break and we have enough strength. The second example problem I'm going to go over is, in this case, we have the 50 centimeter long hollow shaft with outer diameter of 5 centimeter, inner diameter of 3 centimeter. It's made of steel, so E is 200 gigapascal and mu is 0.3. We would like to calculate the applied torque if an angular gauge measurement measures the deformation of 2.5 degree. And we would also like to calculate the power transmitted through the shaft. I haven't talked about that yet. I will shortly. So let's look at the first part of the problem. Really, it's number crunching. We just do a numerical substitution, and formula is given. We calculate G first, knowing E, knowing mu, knowing the formula. Of course, so we are going to try to find this. So E is given, mu is given, and you can simply calculate G. Again, we do basically a numerical substitution, and torque would be Newton meter radian. Make sure you guys note the unit that's used here. Right here. Newton meter radian, because there's also that angular rotation that's involved here. For part B, I'm going to basically introduce to you another formula for power, torque times the radian per second. That's the W that's given here. That is based on the revolution per minute for that particular shaft. In this case, 3600. We just need to convert that into a radian per second. 1 minute, there's 60 seconds in 1 minute, so we go from ReV per minute to pretty much ReV per second. Then from there we go multiply by 2 pi to go from radian to seconds. Okay, so we're going to have a W, or sometimes called omega, of 376.99 or 377 radian per second. We do a numerical substitution again, knowing W and T. We should be able to calculate P. Note the units here. This P is in W. Okay, it's Newton meter radian per second. That's your W. And that, in order to convert that to horsepower, 1 horsepower, we have 746 W there. So that would bring the number would be smaller. We divide it by 746 W. It would be 1,812 almost. That's the horsepower. That brings me to the end of the discussions that I wanted to have today in this recording. If you have any questions, you know how to get a hold of me. Use the course website and discussion board to get a hold of me. Thank you. I'm trying to. All right. Thank you.